Hello students. So this session we'll see about the Ampere circuit law. So from the Ampere circuit law we can also derive the Maxwell's third equation. So first we'll see about what is Ampere circuit law. So Ampere circuit law states that the line integral of H around a closed path is the same as the net current enclosed by the path. I'll repeat. So Ampere circuit law states that the line integral of H around a closed path is the same as the net enclosed current. So we'll see what is the expression for the Ampere circuit law. So I have said a closed path. So since it is a closed path, I have to put an integral and a small circle over it. So an integral and a small circle represents the closed path. So H dot dl. H is your magnetic field intensity and dl is your differential length, which will be equal to the enclosed current. So that is your first equation. So Ampere circuit law states that your closed path, closed integral H dot dl is equal to enclosed current. So Ampere's law can easily be applied to determine your magnetic field intensity H when the current distribution is symmetrical. So the special case of Biot-Savart law only we call the Ampere's law. So we know the Stokes theorem. Stokes theorem is nothing but converting your line integral to surface integral. So we can write the enclosed current is equal to line integral of H dot dl. The same way, when you apply the Stokes theorem, you can convert this line integral to surface integral. So you can write integral S del cross H dot ds. So enclosed current can also be represented in terms of line current, and it can also be represented in terms of surface current. So we know that enclosed current can also be written in terms of the volume current density, that is integral S J dot ds. So this is also an enclosed current. This is also an equation for enclosed current in terms of L and in terms of S. So comparing the equations 2 and 3, we can conclude, since both are enclosed current, we can write del cross H is equal to J. That is, integral S del cross H dot ds is equal to integral S J dot ds. Since both the right hand side and left hand side both as integral S, we can eliminate that, and ds is also common in both right and left side. Therefore, we can eliminate the ds. So the remaining will be the del cross H equal to J. It's nothing but your third Maxwell's equation. So now we'll see the applications of Ampere's law. So the first application we'll see. The first application is for infinite line current. So you see this diagram first. You consider an infinitely long filamentary current I, which is along the z-axis. I'll repeat, you consider an infinitely long filamentary current I along the z-axis. So you need to determine what is the magnetic field intensity at an observation point P. So I keep the point P in space. Okay, I need to determine what is the magnetic field intensity at the point P. Now you try to allow a closed path which passes through the point P. So this path on which the Ampere's law to be applied is known as the Ampere path. So how we call it as a Gaussian path in the unit 1? The same way, the closed path which is passed through the point P is called as the Ampere's path, which follows the Ampere's law. Okay. Now we take, in that Ampere's path, we take a small differential length dl. So the distance between the long filament to the point P is defined by the radius rho. Okay, have you understood the diagram? Now we'll go for the equations. So I is equal to closed integral h dot dl. So I is equal to, since it is a sphere, the radius of the sphere will be 2 pi. Therefore, integral 0 to 2 pi h pi a pi dot rho into d pi a pi. How this you got is, so for a small differential length, we have taken in that Ampere path. So we can write h is equal to h dot dl with respect to the line integral. And then in the place of h, I can replace with h pi and the unit vector a pi. And in the place of dl, so dl, if you see in the diagram, the dl, the differential length is dl is with respect to the rho and the d pi along with the unit vector a pi. So the differential length will vary with respect to rho, that is the radius between the straight filament and the point P, and with respect to the a pi. Therefore, here in this equation, in the place of h, I have replaced with h pi and a pi, the unit vector a pi, in the place of differential length, because differential length will vary with respect to the rho and the pi. Therefore, I have written rho d pi into the unit vector a pi. So in this equation, we can take h pi as common. Therefore, h pi I have taken it outside the integral. And the dot product of the same vector will be equal to 1. That is a pi dot a pi unit vector will be equal to 1. So the dot product of the same vectors will be equal to 1. Therefore, the remaining terms will be rho into d pi. The integral will be, the limits will be 0 to 2 pi. So that will be equal to h pi. Again, the differentiation with respect to pi. Therefore, the rho will be a constant. I'll take it outside. Therefore, if you integrate d pi, the integrated value will be pi. And if you apply the limits, you will be getting rho h pi. Applying the limits, you will get 2 pi. That is higher limit minus lower limit. That is 2 pi minus 0. So there will be, therefore, you will be getting I is equal to rho h pi dot 2 pi. So cross multiplying, otherwise rearranging the equation, you get h pi is equal to, these two terms will go in the denominator in the left hand side. So h pi is equal to I divided by 2 pi rho. So we have missed that unit vector also. Therefore, h is equal to I divided by 2 pi rho into a pi. So this is the first application. Infinite line current is the first application of the Ampere circuit law. So the next application is the infinite sheet of current. So here, see this diagram. You're considering an infinite sheet in the Z plane. Okay, you're considering an infinite sheet. This is an infinite sheet which is in the Z plane. So if the sheet has the uniform sorry for the interruption. So we are considering an infinite current sheet in the Z is equal to 0 plane. So if the sheet has an uniform current density, which is represented by K is equal to Ky dot Ay unit vector, and the unit of K will be ampere per meter. Now we are going to apply the Ampere's law to the rectangular closed path. So the closed path we have 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay. So this 1, 2, 3, 4, 1 will be your Amperean path. So we can give the closed integral. We come to the Ampere's law equation. It's nothing but the closed path h dot dl will be equal to the enclosed current. So in this, the length of this will be the A and the length of this will be the B. Similarly, this is A means this will be minus A. And this is B means this will be the minus B. So H dot dl is equal to enclosed current, which will be equal to Ky dot B. So the current flowing in the y direction. So this is your y direction. So the current flowing in the y direction, the H component cannot have any component in the y direction. So HZ component will get cancelled because the sheet in the XY sheet is in the XY plane. You can see in the diagram, the sheet is in the XY, the sheet lies in the XY plane. So that's why HZ component will get cancelled because the sheet is in the XY plane. So we can write H is equal to Hx Ax unit vector where Z greater than 0 and minus Hx Ax unit vector where Z is less than 0. So you can say, in other words, the resultant differential magnetic field intensity has only an X component. Also, H on one side of the sheet will be negative than the other side. So H for an infinite current sheet will be H into Ax unit vector for Z greater than 0 and minus H into Ax unit vector for Z less than 0. So we all know that by Ampere circuit law, your H dot dl in a closed path will be equal to the enclosed current. So here, where your, in this equation, where your Hx is yet to be determined. So evaluating the line integral of H for the closed path, we can write integral H dot dl is equal to integral the path 1 to 2 plus integral the path 2 to 3 plus integral the path 3 to 4 plus the integral 4 to 1 H dot dl. So we can find H dot dl for this rectangular sheet. So we can write integral for the path 1 to 2 plus integral for the path 2 to 3, integral for the path 3 to 4, and again integral for the path 1 to 4 H dot dl. We need to find what are those things. Okay. So coming over here, so for path 1 to 2, dl, your differential length will be minus dz into az. We know that it lies in the z is equal to 0 plane. So we get minus. Similarly, the path 3 and 4 will be dz into az. So coming over in the diagram, so I said you, this length will be your A. So for 1 to A, depends upon the correct direction. If we represent it as minus AZ unit vector means, in the path 3 to 4, it will be plus AZ unit vector. Similarly, this side also. If you represent in the path 2 to 3, plus plus AX unit vector. And similarly, the other side will be minus unit vector. Okay. So here, that's why we have put for one, it is minus, for the other one, it is the plus. So we can determine the magnetic field intensity is in the X direction, while Ax dot Az, that is, the dot product of two different vectors will be equal to 0. Hence, along the paths, we can write integral H dot dl is equal to integral the path 1 to 2. It is not the integral value, it is the path 1 to 2 minus Hx Ax dz Az plus integral 3 to 4, the path 3 to 4 minus Hx Ax dz Az. The other two paths, that is 2 to 3 and 4 to 1, will be equal to 0. Therefore, we get integral H dot dl will be equal to 0 because the dot product of two different vectors will be equal to 0. Therefore, this will be cancelled and the dot product of Ax dot Az will be equal to 0. So these two things will become 0. When you consider the path 2 to 3 along which dl is equal to minus of Ax into dx, and in the path 4 to 1, it will be plus Ax into dx, we can write for the path 2 to 3, H dot dl will be equal to, in the place of H, I'll replace with Hx minus Hx and minus Ax unit vector. In the place of dl, I'll replace with dx and minus ax unit vector. So this will become hx plus hx dot b. Okay. Similarly, for the path 4 to 1, I will get hx integral dx. So the two paths will get cancelled. That is 1 to 2, and as in the previous equation, the paths 1 to 2 and 3 and 4 will get cancelled. The value will be 0. The paths 2 to 3 and 4 to 1 will be there. So adding upon all the equations, we get closed integral h dot dl will be equal to 2hx dot b. Now we need to compare the equation 1 and 2. What is our equation 1? The earlier we have written. Equation 1 is enclosed current will be equal to ky dot b. Now what is the equation we have got right now? It is closed integral h dot dl, otherwise the enclosed current will be equal to hx dot b. Now we have to equate or compare the equations 1 and with this equation 4. Therefore, ky dot b is equal to 2b hx. So from this, you rearrange the equation, you get hx is equal to ky divided by 2. And now you substitute this fifth equation in equation 1. What is equation 1? H dot dl equal to A enclosed current will be equal to ky dot b. So you substitute this in the place of h, you substitute this fifth equation, therefore you get h is equal to 1 by 2 ky az unit vector where z is greater than 0 and minus 1 by 2 ky az unit vector where z is less than 0. So rather than having a specific axis, that is x-axis, ax unit vector, generally we can write for infinite sheet of current, the current density K having the unit ampere per meter, we can write the magnetic field intensity H is equal to 1 by 2 K into AN unit vector, where AN represents the normalized unit vector directed from the current sheet to the point of interest. So the next application we'll see in the next session.